Okay, so welcome everybody. I suggest we start the session. So it's my honor to introduce the first speaker, Don Page, please.
Yeah, thank you. It's a great joy to be back here. It's my fifth trip to Israel. I think I first went to conference 79 to 80 about, some quantum cosmology stuff. Jim Hartle was giving a talk about, and he first talked about the Hartle-Hawking no boundary wave function, and then he decided he was going to talk about some others. He said, well, the Hartle-Hawking one isn't ordained by God, so let's also consider another one. So I spoke up and said, well, if it's not ordained by God, does that mean it's not correct? And then Stephen Hawking spoke up and said, it's the only one not ordained by God. So anyway, I don't know. Okay, and then this, anyway, just a scene from top of Mount Temple, which is near, not about 5-hour drive from Edmonton. So anyway, we got some nice scenery in Alberta, so welcome to come sometime to the Canadian Rockies. Okay, today I want to talk about, well, first mention what I call the complete theory of the universe, but this is the same as what Eddie Chen was talking about, a strongly deterministic theory. It would not only give a complete set of dynamical laws, what has been misleadingly called the theory of everything, it's not until you get other parts, but also the quantum state of the universe, which Hartle and Hawking have made one proposal for it, and Eddie Chen had some other proposals, and the so far unknown rules for extracting the probabilities of observations from the quantum state. Now, I'm going to distinguish that from the probabilities of the branches, which Everett and Hartle and Saunders and others have given. For that, I'm saying the probabilities of observations is not the same because you can have in one branch, you could have different numbers of one kind of observation from another. So the probabilities of observation can differ. Now, I'm going to propose a basic framework for these rules, rules you could say of psychophysics, for these rules that the measure for each observation is the expectation value in the quantum state of the universe of a corresponding positive quantum operator for each possible observation, which I shall call an awareness operator. Now, one needs to say what observations are, and I propose that they are fundamentally sentient experiences, each being the entirety of a conscious awareness, all that one's consciously aware of at once. And I often use conscious perception as a synonym for sentient experience. So if I say sentient experience, I mean the same as conscious perception, all that one's consciously aware of at once. And I shall point out, but I don't have time in this talk to explain, that for a large universe with indistinguishable copies of observers, the quantum awareness operators cannot be projection operators, as one might have assumed from Born's rule. So Born's rule does not work in a large universe, or as one of my papers had it, the Born rule dies. Now, bare quantum theory describes the universe in terms of quantum states, operators, expectation values, wave functions, amplitudes, path integrals, etc., but it does not by itself connect these to observations. So bare quantum theory is not directly testable. To make comparison with observation, Max Born suggested that the wave function gives probabilities. Later, it was proposed that the probabilities are given by the absolute squares of amplitudes, and these can be taken to be the expectation values of projection operators. So in this talk, I shall take the mathematization of Born's rule to be the idea that the probabilities of observations are given by the expectation values of projection operators, though I'm going to reject that view, but that's what I'm. If I say Born's rule, I mean that expectation that the probabilities are given by the expectation value projection operators, but I'm going to deny that that's the case. Okay, now let's consider a Bayesian analysis for probabilities of theories. So consider theories T sub I, that for each possible observation O sub k, each theory T sub I gives a probability for that observation. P of O sub k, and that bar means given T sub I. Given T sub I, what's the probability of the observation? Now to get to, but we want the posterior probability, which is the probability of the theory given the observation, and for that we need to use Bayes' theorem. If we assign what seem to be inevitably subjective prior probabilities, P sub t, to the theory C sub I, presumably higher for simpler theories by Occam's razor, and if we use an observation O sub k to test the theory, then P, the probability of the observation given the theory, is what's called the likelihood of the theory, But remember, that's not the probability of the theory. It's called the likelihood, but it's the probability of the observation given the theory. And by Bayes' theorem, we can calculate the posterior probability of the theory, the probability of the theory given the observation, as the product of the prior probability times the likelihood, and then normalized by dividing that that same expression, but summed over all theories. So we would like to get this posterior probability as high as possible by choosing a simple theory for high prior probability that gives a good statistical fit to one's observation, so high likelihood. Now, since a complete theory of the universe should completely specify all properties of the universe, one might think it has no room for probabilities between 0 and 1. So all likelihoods would be 0 or 1. Then the posterior probabilities of these theories, given the observation OK, would just be proportional to the prior probabilities of the theories that give that observation as having 1 instead of 0. But for observations, even though I'm a theorist, I do think science is fundamentally, or maybe primarily, I don't know, observational, physics observational science, so I want observations to play a bigger role. So we'd like a way of getting a range of likelihoods between 0 and 1. So now, if the theories can give normalizable measures for the observations, then the normalized measures can be interpreted to be used as if they are likelihoods that can vary between 0 and 1. So even if this complete theory determines everything, so it's deterministic, there's no room for uncertainty or probability within the whole theory, but if there are these measures, they could be used as if they were the likelihoods. So in a classical theory, for example, the measures could be functionals of the phase space trajectory, such as the amount of time that a system spins in each different region of the phase space. In quantum theory, the measures could be certain functionals of the quantum states, or maps from the quantum states to non-negative numbers. Now let me give another argument against likelihoods all 0 or 1. If a specific theory leads to the definite existence of more than one observation O sub k, as indeed many worlds does, or even the single universe does, because there's lots of observations going on, one might be tempted to say that the likelihood, the probability of the observation given the theory is 1, since it exists for all these observations. That would give unit likelihood for any theory predicting the definite existence of the particular actual observation used to test the theory. However, this procedure, or this assumption, would mean that you can construct a theory of maximum likelihood, which is 1. I mean, the likelihoods can't be bigger than 1, no matter what the observation turns out, just by having the theory predict that all possible observations definitely exist. But this seems to be too cheap, supposedly explaining everything, but actually explaining nothing. So, I mean, some people say, well, the multiverse, since everything exists, it explains why we see it. No, we need more. We want to get the probability of our observation and then multiply by the prior and get the posterior probability, which it's not sufficient just to say that the theory predicts that our observation definitely exists. So therefore, I'm proposing the normalization principle, or meta theory, that for each theory T sub I gives normalized, quote, probabilities, or really measures, but quote, probabilities, for the different possible observations that it predicts. So for each theory, the sum of these likelihoods over all O sub k is unity. So there's a trade-off between prior probabilities and likelihoods. There's prior probabilities for the theories, that's the intrinsic plausibilities of them. In this case, for the whole universe, before you have any observations, which is really impossible for us within the universe. Then there are the conditional quote probabilities, or measures, for the observation given the theory, so what are called likelihoods of the theory for fixed observation. And then the posterior probability, the probability of the theory given the observation, proportional to the prior probability times that, and then, of course, normalized. So the prior probabilities are subjective, usually higher for simpler theories. So in my mind, the highest prior probability might be for the theory T sub 1, that nothing concrete or contingent exists. But then, since our observations are certainly contingent, I mean, they don't logically need to exist, then the simplest theory would predict that there are no observations. So then the probability of the observation would just be 0, and of course that then, by this up here, it leads to zero zero posterior probability. I think I can say there's zero probability that nothing concrete exists. T sub 2 might be the theory that all possible observations exist equally. But then, since surely there's an infinite number of possible observations, to normalize it, you'd have to take the 1 divided by the number, and that gives 0 when normalized. So that would be my argument against, if you extended modal realism of David Lewis and Novak's or whoever else proposed that everything logically possible actually exists, if you augment that by saying that everything actually exists with equal measure, all possible observations, then this rules it out, because it says that the probability is diluted among an infinite number, so there's zero likelihood for our observation. Now, the other extreme would be a maximal likelihood theory, giving the probability of the observation given the theory of 1 for one's observation O sub k. But of course, since I'm saying the sum over all observations has to be 1, that means there's no measure for any other observation. So it's saying that only one observation exists. And this, if I imagine my own observation in it, it's got a lot of order and complication, and there's a lot of details in it. I would think it would require a very complex theory to predict that only my observation exists and not any other ones, not any of yours, or not any of mine that I think I had in the past, and so on. So okay, so I would assign that an extremely tiny prior probability, giving a very low posterior. So this is a trade-off between prior probabilities and likelihoods, that is, between intrinsic plausibilities and fit to observation. Okay, so probabilities of observations. I'll take an Everettian view that the wave function never collapses. So in that sense, I'm an Everettian. At the end, I might ask you to see, based on my talk, whether you consider me an Everettian or not. But anyway, for now, I'm Everettian as far as I believe there's no collapse of the wave function. The wave function never changes. So in the Heisenberg picture, there's only one single fixed quantum state for the universe. And the universe might be a multiverse, might have different parts with different effective coupling constants and so on. I assume that instead of, quote, many worlds, or instead many different actually existing observations or sentient experiences O sub k, but they have different positive measures, mu sub k, it depends on it's a function of the O sub k, which are in some sense how much the various observations occur, but they're not determined by just the contents of an observation. The measure of a toothache is not how painful it is or anything. It's not the content, but it's a measure. It's kind of a primitive concept. I don't have some other analogy, but I mean, if you wanted to think of an analogy, not that I'm doing it, but you might think that, okay, maybe God in his time is thinking in a sequence of all the possible observations, and the amount of time he spends on each one is proportional to this measure. Now, I'm not taking that picture literally, but I'm saying the measure is kind of a primitive notion here. So what the measure of observations, I can't say it's like an electric field or a scalar field or mass or energy or anything else. It's just a measure. It's just a fundamental concept in here. Now, for simplicity, well, to avoid having to bin things, I shall assume there's a countable discrete set, O sub k, of observations, and the total measure is normalized to unity for each possible complete theory that gives the normalized measures for all possible observations. So then in a Bayesian analysis, I shall interpret the normalized measures, each theory, as the, quote, probability of that observation given the theory, which for one's observation O sub k is the, quote, likelihood of the theory. So I'll use those as likelihoods. Okay, now we get to my framework for what these measures are. The map from the quantum state to the measures of observations could be nonlinear. And I think in some sense, if you required some definite proposal for what the branches are, that would be nonlinear in the thing. So I think you'd end up with nonlinear measures. But I'm going to assume a linear relationship in what I call sensible quantum mechanics. I also, in a paper for Lehman, I called it mindless sensationalism, because it proposes what's fundamental is not minds. It's not a many minds theory like Lohr and others, but conscious perceptions, which crudely might be, well, I stretched it to make the title, might be called sensations. Well, of course, a conscious perception includes more than just the sensations. It includes memories and emotions and thoughts and a lot of other things besides sensations. But anyway, just to get that phrase. Okay, so the measure for the observation is the expectation value. Sigma is a quantum state that gives expectation values to operators. So it's there for each observation, there's a positive operator, or I could just say the operator, I could condense this to say A sub k is the operator corresponding to that observation, and the brackets are expectation value. It's the expectation value of O sub k, which is the same as this. So sigma is the quantum state of the universe, interpreted as a positive linear functional of quantum operators, and A sub k is a non-negative awareness operator corresponding to the operator observation or sentient experience, or in other words, conscious perception O sub k. So the quantum state in this could be a pure state, it could be a mixed state given by a density matrix, or it could be a C-star algebra state. It basically just needs to give expectation values of operators. And the awareness operators, along with the linear relation above and a complete description of this, the theory would also have to say what's the content of each of these observations. Would all be given by this complete theory. Of course, we don't have the theory, but I'm trying to give a framework for what I would believe could be a complete theory. Now, I've shown elsewhere, I don't have time to describe it here, Born's rule does not work in a universe large enough that there may be identical copies of the observer at different location. If you have one here with a part with spin up and another one with seeing spin down, they should assign probabilities between 0 and 1 for that because they're not certain which one they are, but there's no projection operator that would give that, at least if you could allow fixing the projection operator first and then having the state change. In other words, I think it's what's called non-contextual, I guess, projection operators. Okay, so the failure of Born's rule means that in this theory tested by the awareness operators, whose expectation value in the quantum state sigma, so I of the universe give the probabilities or quote probabilities or normalized measures for observations of sensing experience as this formula, which I'll repeat here, they cannot be projection operators. However, they could be weighted sums or integrals over space-time of localized projection operators, p sub I, but depends on x that denotes the location in the space-time. Say under brain states there that would produce the observation. So part of it, one of it might be a projection operator on what's going on in my brain, and a suitable state of my brain that would lead to my present conscious awareness, for example. So now there is, okay, I would not expect that the theory to say exactly where each one of these is, so I'd expect there would be some integral or sum. It could be looking, maybe if it's looking in here, that contributes a significant part to the expectation value. If it looks over here, it would be, exponentially, enormously suppressed. I mean, I suppose there's some quantum amplitude for a brain to appear here, Boltzmann brain, and so on, but very negligible, and then so on and so on. But if I do the integral over all space, eventually somewhere, if it catches a brain somewhere, then it will get contribution there. But now there is a problem because our universe seems to be expanding exponentially or asymptotically exponentially and might go on forever, that in local quantum field theory with definite globally hyperbolic spacetime, any positive localized operator, such as a localized projection operator, will have a strictly positive, that is non-zero and non-negative, positive expectation value and any non-pathological quantum state, including the vacuum. So if such a positive localized operator is integrated with uniform weight over a space-time with infinite form volume, it will give an awareness operator with infinite expectation value. I won't be able to normalize it. So integrating up over all these regions, even though after the stars have all died out and us ordinary observers, or OOs as people call it, have died out, there's still in some region of space, it's even no matter how empty, there's still possibility of a quantum fluctuation so that this operator will have a positive expectation value. Maybe very small, maybe 10 to the minus some huge number, but non-zero, and if you integrate that over infinite form volume, you'll get infinity. Now you can say, well, we'll cut it off at some finite cutoff time t sub c, and then you normalize it. Then for universe, it continues forever with a 3 volume bounded below by positive value. So in other words, the 4 volume is growing indefinitely. The intervals will be dominated by times of the same order of magnitude as the cutoff time. And so at these late times, the probability, if it's sufficiently late that the probability per 4 volume of ordinary observers is very low, then most of the measure will be contributed by thermal or vacuum fluctuations, which are so-called Boltzmann brains. That is, Boltzmann brains will dominate the measure for observations if you just do a uniform integration over space-time and then cut it off at some place and then normalize it after that. Now, if Boltzmann brains dominate the measure for observations, one might ask, so what? Couldn't it be their observations are those of ordinary observers? Or couldn't it be their observations really are Boltzmann brains, but they look like things look ordinary? However, my argument against that is that since Boltzmann brain observations are produced mainly by thermal or vacuum fluctuations, it would be expected only a very tiny fraction of their measure would be for observations so ordered as ours. It'd be very rare for Boltzmann brain observation to have all the order that I have in mind, of seeing faces that I recognize and correlate with memories of how I remember you looking yesterday, or in some cases even decades ago. So anyway, so there's a very tiny fraction of the ordered Boltzmann brain probability, plus the even smaller fraction of ordered ordinary observer observations, assuming that they're dominated by the Boltzmann brains, in comparison with the dominant disordered Boltzmann brains, would be only a very tiny fraction of the measure of all observations. Thus, the normalized probability of one of our ordered observations, which we would use as the likelihood of the theory, would be highly diluted by the other, because remember, I'm requiring that the sum of these measures adds up to 1. And so if most of it is for the Boltzmann brains, then it only leaves a small, most of it for the disordered, leaves only a very small part of the probability for the ordered ones. So it'd be much smaller than alternative theories in which Boltzmann brains do not dominate. So if you could come up with alternative theories that do not have prior probabilities that are too small, they would dominate the posterior probability over the naive ones that have this Boltzmann brain domination. Now, other observations that seem at least naively difficult to explain by Born's rule include our observation that we are humans rather than ants, despite the much greater number of ants on Earth. Again, if each ant had as much measure of consciousness as we do, then the probability would get diluted by all the math. If we had to sum up the unity, and so it would be, it would be improbable that we find ourselves to be humans. Not as bad as the Boltzmann brain. I mean, the ants don't outnumber us near as much as the volume of space-time compared to the early time. So it's not near as severe a problem as that, but it still seems to be somewhat of a problem. Okay, as we shall see, modification of Born's rule can explain the probability of observation by copies of the observers. Well, okay, I won't get into that part here, I guess, but the fact that we apparently do not observe ourselves to be Boltzmann brains and the fact that we do not observe ourselves to be ants. However, it's not yet known when the correct modifications are, so there's many logical possibilities for the probabilities. I do think the universe really does have one particular rule. It has one thing, and I'm conjecturing that it has this form, but exactly what the awareness operators are, I don't know. So there's many possibilities that seem to be logically possible, and it would, of course, we would like to learn which is actually the correct one. So, yeah, the main open question in the sensible quantum mechanics framework, in which the quote probabilities of observations or the expectation values of positive awareness operators, one corresponding to each observation, is what these awareness operators are. So this SQM framework does not assume there's a space-time, so it could be valid even in formulations of quantum gravity in which space-time is not fundamental. However, to kind of tie it a bit to what we presently know rather than what we don't yet know, if the part of the quantum state that gives the dominant contribution to expectation values of the awareness operators can lead to an approximation of an effective space-time or of a quantum superposition of space-times, one idea is that the contribution to the expectation value of an awareness operator from each space-time in the superposition, well, first, the expectation value of the existence of this space-time, that would be similar to the probability for the branch, if each space-time has its own branch, multiplied by a weighted sum or integral over the space-time of localized projection operators for each region of the space-time. So to avoid Boltzmann brain domination in the sum integral, it seems necessary to choose weight factors that get convergent integrals that are not dominated by the asymptotically empty regions where almost all observations would be by Boltzmann brains. So for space-time with preferred spatial hypersurfaces, such as proper time t from a Big Bang or from a bounce minimal hypersurface, that at each time have finite free volume, though perhaps tending to infinity asymptotically with time. One simple procedure for avoiding divergent integrals over space-time is to divide the contribution over each of these preferred spatial hypersurfaces by its 3 volume. Then that gives taking the contribution at each time to be the volume average of the expectation value of the localized operators there. So that would mean that at each time at later would only give a finite and at late times a very tiny contribution to the awareness operators. But there's still a problem with the thing diverging if you integrate from t going to infinity. So here I propose something even more ad hoc to replace the integral over dt, which diverges, by an integral over dt over 1 plus t squared. I call this Agnesi weighting because that curve, well, it's the Lorentz line shape or the Cauchy distribution, but in old times it was called, the curve it was called the witch of Agnesi. I'll tell you later the story about how it got the name witch, but anyway. Agnesi was a female mathematician, but there's no suggestion that she was a witch, but the curve got called the witch of Agnesi. Well, I can say it's due to a confusion between the Italian words for witch and for curve. So I guess a witch is a twisted person, so I guess the words, are similar. I don't know Italian, so I don't. Okay, now this last part's admittedly ad hoc. The other is a little bit ad hoc, but less so than this. So it should be a more elegant formation, should be found. So then to explain why we observe ourselves to be humans despite the much greater number of ants, it seems plausible to postulate that human brains are much more efficient in producing sentient experiences than ants. So the total probability of human conscious perception is not far below that of ants to make human observations much less probable. If it's half and half, I don't care. It doesn't make much difference if the probability is reduced by a factor of 2, but if it's reduced by a factor of millions, then I start worrying about it. Therefore, one might postulate that the localized projection operators, the human brain configuration, should be much given weights, W sub k, than the localized projection operators, the ant brain configurations. Perhaps part of this weighting factor should be the complexity of the corresponding human brains, since human brains seem to be much more complex than ant brains. But I'm skeptical of the hypothesis simply getting high complexity or high information processing is itself sufficient for getting large weight multiplying the corresponding localized projection operator for the corresponding awareness operator. So just making a computer as complex as the human brain, I don't think that implies it's conscious, or it has a significant measure of consciousness. I think everything has some exponentially tiny measure of consciousness because there's always some amplitude for the region in there to be a human brain configuration, for example. Okay, so to suppose the expectation value of a given space-time is E sub S sub L is E sub L, that might be, if you say that each different space-time is one of the branches, then that might be the probability for the branch. And that in this space-time, the expectation value of the localized projection operator corresponding is this, that the expectation value as a function of the space-time position. Suppose further that this space-time, the weight factor for the integration over 4 volume is capital W as a function of, for example, it could be 1 divided by the volume of the space at that time, and 1 plus t squared to avoid the integration. And that the intrinsic weight factors for the observation is little w sub k, that's the one that makes humans better than ants. Then the relativity of probability could be, the relative, that's before I normalize it, the weight factor for human ones, a sum over all the space-times with their expectation values, and then over each space-time an integral over the 4 volume, but then with this weight, this position dependent, but diffeomorphism invariant. I mean, it depends on the actual properties of the space-time. So diffeomorphism invariant, but it's a non-local because it depends on, for example, the time since the Big Bang or the volume, this weight factor, and then the density of the expectation values. Okay, so then this formula shows, because we don't know what the little w's or the ELs maybe you can calculate, and the capital W's. So there's a lot of logical freedom in the modification of Born's rule for cosmology, even within the restrictions of sensible quantum mechanics, in which the relative probabilities of observations or expectation values of the positive quantum operators that are the awareness operators corresponding to the observation. There would be even more logical freedom if you abandoned this and allowed the relative probabilities to be nonlinear in the expectation values, such as these expectation values raised to a power s that is different from unity, or to be even more general nonlinear functionals of the quantum state. So therefore, in sensible quantum mechanics, what can be used instead of quote, probabilities of observations are instead measures for many actually existent sentient experiences, each given by the expectation value of the quantum state of, in the quantum state of the universe of a corresponding positive awareness operator. The awareness operators cannot be projection operators as suggested by Born's rule, but in a space-time picture, they might be given by a suitably weighted integral of localized projection operators within each space-time and then summed over space-times weighted with their quantum expectation values. There's considerable logical freedom in these weightings, so we are far from knowing what is actually the case for our universe or multiverse. So this talk was largely a summary of this paper, and I was grateful to discussions with Sean Carroll and his idea of Stebbins, the hospitality where some of these ideas were developed. And I want to ask you whether he's right in saying this. He emphasized that by sensible quantum mechanics framework, with the relative probability of observations being the expectation values of positive awareness operators, is not Everettian quantum mechanics, which he says assumes a particular branching of the quantum state and probabilities of observations depending on this branching, and that would be highly nonlinear functionals of the quantum state if you have to specify how the branching is going. So, okay, so that's my conclusion. I might ask, how many of you think, having heard these sort of radical ideas, or whatever, how many would say that I'm an Everettian? How many was, okay, 1, 2, 3, 4, yes? 1, 2, 3, 4. How many would say I'm not an Everettian? Oh, it's one, maybe one. It's a little indefinite. Okay, well, I hope people excuse me if sometimes I say I'm certainly never ready, this is no collapse. And the other thing, of course, I'd certainly appreciate it. I know these ideas are very speculative, and they're not going to be able to be fully developed, probably within my lifetime anyway. But if anybody knows of some way to show that they're definitely wrong, I would definitely appreciate being shown if something is wrong. Well, and any suggestions on how to go further in this direction. Thank you.
Thank you. Thank you very much.
There is one thing which I liked very much. What I believe we need formalism, the first year assumption, there is no collapse. And then we need additional rule, which is connect to our experience.
Right.
Which I think you believe it, you defined it as a theory.
As a what?
Theory. You have some theories. Is your theory is this rule, yes? The theories which you discussed, different theories.
Right.
These are these rules connecting the universal wave function to our experience.
Right.
Correct? And then we need this awareness.
Right.
But what I think all your troubles, there is a standard, I am local person. I need only local awareness operator. And then I think in one moment you said, if you put it local, then everything is okay. There is no problem. And there is no problem. Just put it local. There is no awareness operator. It's projection, of course, local projection, that I'm here, I have particular experience. And this will help me in only these special cases when somehow I'm in this situation that I'm aware where I was before. Now I have 2 rooms to be. Then I will use my expectation here and expectation there to make my prediction. And then if it's local, there will be no problem with the Born rule, no problem with everything. So it just seems the idea that in the beginning you said your awareness operator is global, the same for everyone. No, awareness operators should only it's for us. It's subjective, so you have to make it very, very local. And then, of course, Ant will have his awareness operator, and he will use it, and this will be a Born rule, which is your probably calculation will show that the Born rule is the best. But no, this is a bit beside the point. First, just make it subjective for every sentient being. Don't put it's everywhere. Don't make integrals. Don't put this Boltzmann brain all over. They're not important.
Well, partly this is motivated by problems in cosmology, the measure problem in cosmology, how to get finite probabilities for observations from in a multiverse. If the universe is a multiverse and you have different spacetimes that have infinite volume, how do you I mean, there's a problem of how you regularize that. And even if you said, well, we'll take some fixed 4 volume, But then if you compare it to some other universe that has entirely different coupling constants, what do? Well, maybe you could do it in Planck units and that. Anyway, they're very difficult problems, and I think I'm not necessarily saying I'm going to be able to solve these problems, but I think you need some framework like this to calculate, because you like to see what's the probability of different cosmological theories to predict our observations, not just what's the probability that we get result A or result B from some local experiment. I agree that the Born rule is a very good approximation for that sort of thing, because these, this integral over the weight factor is not going to change much on a human time scale. But if we're interested in cosmological problems of what's the quantum state of the universe, and what's which may be a multiverse not only having different Everett branches but also different effective coupling constants, then we need more to explain that. And I'm just trying to say this is a framework for trying to explain it. Of course, it's not a theory until we have the awareness operators.
So exactly, just to mention, there is this conference about many words interpretation. And there is multiverse, a cosmological multiverse, which I also have kind of many words, but this completely different story, different subject, and it seems that you put them together, and then I think it should be separated clearly. Well, what we're discussing. So we don't discuss cosmological and other things. So you say Born rule is dead. This is because you talk about multiverse. Cosmological multiverse. If you talk about many words in one without cosmology, then it doesn't work. But your papers look like the Born rule died. If I understand correctly, it died because if you consider cosmology, not it died if you consider.
Yeah, it died with cosmology, but you only need a single universe large enough. Well, it has to be enormously large to get copies of observers, and then it doesn't work there.
No, but then it's again. We need probability in each one of them.
So this was a really rich and provocative talk, and there are a lot of things I want to ask you about the role of sensation and the role of cosmological no-hair theorems in the cosmological setup you're using, but I think those are really long conversations. So I want to actually have a follow-up on what you just were, one of the things you were you said in response to Lev about the measure problem.
Right.
You don't just want a normalized measure. You also want it to be the case that that small perturbations don't change measure very much. So in some sense, you want something like a translation invariant measure.
Right.
You also want it to be the case that like large measure corresponds to open sets in some reasonable topological sense, and small measure corresponds to meager sets or something like that. So you also want a Borel measure. And you also want these two to play nicely together. So what you really want is a translation invariant Borel measure. I mean, forget normalizable. But I mean, on these big spaces you're talking about, there are very powerful theorems that tell us that you just can't have a non-trivial translation invariant Borel measure. So I'm very skeptical of these kinds of arguments in cosmological settings that say, well, we don't know how to define a measure, but let's just assume there is one. I don't think it's legitimate to say, let's assume there is one, given these very powerful mathematical theorems that tell us there aren't, at least of the kind we really want. So I think I really would like to hear more about how you think we can get around these theorems.
Well, that was the thing. I'm assuming it's not translation invariant, particularly in time. That there is some.
No, I mean translation invariant in the sense that when I make small perturbations to my space-time model, translation invariant in the space of models, not in the space-time. So that if I make a small perturbation and get a model that is in some sense very close to the original one, I'm not changing the measures very much.
Okay, I'm a little confused why I need that. If there's one correct theory, why can't you use, in principle, the correct measure for that, and you don't have to worry about. In fact, I would hope that the ultimate theory would not have any continuous parameters. String theory doesn't have any continuous parameters, and I would hope that the ultimate theory doesn't have any continuous parameters. So there's a discrete set of these possible theories. So I don't think you have to worry about small perturbations of the theory.
So you don't even worry about that small changes in your awareness operators should give you things that are close in measure? You don't even want that?
Well, No, I'm not denying that, but
But then
it
you
seemed
do
like
need
that
to
you're
translate
getting
the
into a
variance.
problem that of course it's not normalizable if you have uniform over some infinite space or something. And I'm saying that was the point of these admittedly present, not very elegant proposals. Well, the volume averaging is not too inelegant. The easy weighting, of course, it's just the simplest function that gives a finite integral. So, but those were things that specifically designed to get the measure finite, even after integrating over infinite t.
There's something that, if we go back to the very beginning of all this, that you put up, that many people have put up. I'm not, particularly pointing you out. People do it all the time. When you put up Bayes' theorem, and you've got conditional probability of O on T, and there's this idea that, well, gee, the P of O on T, that I can kind of calculate.
Right.
What I'm really interested is, in some sense, P of T on O.
Right.
But Bayes' theorem is just a theorem about conditional probabilities, and the O's and the T's are just letters. Now, what happens, I think, is what also happens in the way you've presented this, which I just think is wrong. In the normal sense of a theory, like Newtonian mechanics is, say, with gravity, is in the normal sense of a theory. It does not assign any probability to any observation. Why? Because the theory just gives you the dynamics.
Right. See, I'm talking about a more complete theory.
Anything. It's consistent with the theory. No measurements are ever made. No conscious being.
Yeah, that's
exists.
precisely my point. That you not only need the dynamical laws, you also need the quantum state and the rules for extracting it. So the theory, in my sense, the complete theory is not just the dynamical laws. So Newton's theory is not a complete theory.
But then Bayes' theorem, as you've written it, doesn't really apply. What Newtonian theory will give you is something like a conditional probability for, as I said, two balls to hit the ground together, conditional on the theory and on the initial condition, which was earlier in time, that they were let go at the top of the tower at a certain time. Now that requires, and this is why I said I didn't think you were a many worlds person, that requires there being a temporal transition from the initial condition. This is the way we do experiments.
Right,
We
right.
think, okay, I know this much about how the experiment was set up. I have the theory. I use that now to make a prediction about how the theory will come out. And that requires, of course, that you have something like a branch, even in standard Everett. You've got these
Right.
branches that
Right.
connect the state at one time to states at earlier times. Without that branching, I don't even know how to make sense of a probability like that, right? I mean, there's
Okay.
the Bell many worlds where you're kind of jumping around in those conditional probabilities.
Right, okay.
So I think there's just a tremendous amount that goes into how we extract what we call predictions for observations, which may be statistical for various different reasons, from a theory that are not represented well in Bayes' theorem. And therefore, if you start with Bayes' theorem and say, well, I'm going to start with that, if it's a deterministic theory, I mean, you said if it's a deterministic theory, they're all ones and zeros. Well, no. Even if you give me an initial, I mean, I don't know. So I think the connection between that very first ansatz and the way predictions are actually made and tested, there's a lot more detail in there that is not represented in this very abstract.
Well, admittedly, this is using Bayes' theory for the whole theory, not just for some conditional probability of something, within the universe. So admittedly, this is using, but I don't see any particular reason why Bayes' theorem couldn't be used for P sub t being the entire complete theory that completely specifies everything, and all the branches of the Everett thing, and then all the awarenesses. So I don't know if you have some strong reason for saying the Bayes' theorem. I agree this is not where it's usually used. Usually it's used in partial. We make some observation in our branch or something, and we see something, and then we make some prediction, and then we test it. We get conditional probabilities out. I agree that this is a much broader use of. Well, I don't know. It's broader. It's a much more global use of it because I'm applying it to the complete theory out of some countable set of complete theories.
Let me try this. What we actually do, I have an initial state, which is we might call observation. Right?
Okay.
Bell would say
Yes.
The initial state is, oh, the settings were this, and there were these currents, and blah,
Right,
blah,
right.
blah. Usually, that description is consistent with many different descriptions at the fine-grained physical level that the theory operates on, like in Newtonian mechanics,
Okay.
a precise phase point. Okay? So what do I have to do? I go from the initial description. I then go by some probabilistic map from that to a distribution over, say, phase space points. Then I use the theory to evolve those phase space points, maybe deterministically, maybe stochastically. And then from that, I extract a probabilistic prediction about the outcome, okay? And that's clearly what we have to be doing, and a lot of probabilities get in there that don't even have to be dynamical, right? Going from the macro description of the initial state to the micro description that I need to feed into the dynamics, then evolve it by the dynamics, then extract from that a macro description which corresponds to what we call the observable outcome. It's just there's a lot of, you have to do all that stuff to actually make predictions in the way that predictions have ever been made in the history of physics. Nobody has ever said, oh, this theory just says there's a probability of 8.5 that there'll be a sentient, a sentient experience of such and such a kind, right?
Yeah, so I agree. If you want to do once you focus on a particular theory and then you want to test within it, you say, conditional upon my being aware that I set up the apparatus and such, what's the conditional probability that I got this result? So I could put that in there. What I'd have to do is then I'd have a particular theory. Then I'd have I'd have the probability of the observations in which I have a memory of having set up the apparatus and such a thing. And then, so that's a whole bunch of things that have some probability. And then in the numerator, I take the smaller set of perceptions where I perceive not only that memory, but also a particular result of the experiment. So it's true. I could do something, in principle, I could do something like that once I have a theory for inside the theory. Here, I was doing it in just the broader sense of trying to decide of trying to get posterior probabilities for the theory.
While we get the next question, can please next speaker come and sit up?
So this is kind of indirectly related to a different way of asking Tim's question in some ways. I mean, how would you think about
you can take
deriving just some sector of ordinary quantum mechanics from this?
Sorry.
How would you think about deriving some ordinary section of quantum mechanics from this? I mean, if this is our complete cosmological theory, we'd better be able to get out of it as appropriate special case situations, just mundane things like two slit experiments and magnetic moments and things. I mean, and there, as Tim says, the things we seem to want to get out would end up being conditional probabilities rather than unconditional probabilities. I mean, I could see the internal coherence of the scheme, and I'm sort of trying to work out how to relate it to the extant empirical data for quantum mechanics.
Well, I think similarly by how I was trying to answer Tim, that you could, if you did it in this scheme, then you'd have some observation. Well, you do the experiment, and then because you want to be aware of the result, at the end you'd assume that you're aware of the result, but also of how you set it up.
Yes.
And then so there's a set of different, because I could be aware of other things
Yeah.
too, of like whether I'm hungry or not or so. So there's going to be a measure of a whole bunch of things that that include the awareness of how to set up this. So that's going to give me some measure in the bottom,
yeah.
and then on the top I put the where I also am aware of the results of the experiment.
So you're sort of flattening the conditionals down to absolute probabilities of memory sequences or something like that.
Yeah. So something. Yeah.
Thanks.
Thank you very much.